So what we're going to continue our the last time we did basic description of how we describe linear vector spaces. How we defined, if you remember, fields and vector spaces. So vector spaces we had defined. We had some elementary operations which we defined, and if we impose those operations in terms of linear combination of vectors and scalars, vectors in terms of those bases which were described by composing those number fields and certain operations were defined in terms of, and accordingly we define vector spaces. So vector spaces can be finite dimensional or they can be infinite dimensional. So in our cases we are interested in the finite dimensional vector spaces as such. And in our today's class we are going to we'll have some properties by which we can define something called linear dependence as well as linear independence of these vector spaces. So we said that we normally are interested in principle. When we define the vector spaces, it can go for n dimensions. For geometrical considerations, we took n is equal to 1, 2, and 3. Because you can imagine these operations in terms of geometrical constructions, whether it's plane, line, surface, or volume. That's more that visual intuition helps us in relating these vector spaces vis-a-vis them. So now we are going to have a general consideration how these vector spaces can be defined in some general sense. In some general sense means, for example, if we have, for example, in terms of notation, for example, we are going to define, if we define things. So definition. So normally in mathematics, it should always resemble, we define things. And then the implications of those definitions. When we impose some rules on those very definitions, prior definitions. So the process of defining things is very much. So we first define how we define things, how we can construct linear dependence. So in terms of a definition, if I write it, a finite set so since we are interested in the finite vector spaces, so that's why we can have also an infinite set or finite set of vectors is linearly dependent if there are or if there exists a corresponding set of vectors, set of scalars. Not all zero, so that's important. Not all zero. So the scalars can be or cannot be zero. So that's the point, that's the main point. So such that. So how we define previously, for example, before what we mean by this, for example, we have for each set of indices, you can have this indices, it goes from 1 to n for these set of vectors. First we define any indices. Since a finite indices, we don't take n as an infinity. N can be 1, 2, 3, 4, whatever. So any linear combination of these things, if we multiply a scalar by this vector, and the vector spans from this to n may be any finite number, and maybe if we just have a geometrical intuition to and maybe any finite dimensional space, vector space, which is, and if there's a scalar multiplication to it, if there's a, so any linear combination of these two things, if even if it's zero, it doesn't mean this alpha I is always zero. That's the point. So the point emphasizing is, if you multiply any vector space, a finite dimensional vector space, and multiply it by any scalar, so the combination of them, even if is zero, it doesn't mean this alpha I is or this scale is always zero. So this is the finite subtle sense. So if it is not zero, so there are different ways of arriving at zero. In case this alpha I is not explicitly zero. If it's explicitly zero, then we have a linear independence, a condition called linear independence. It's directly, if this is zero, so this will. So there are cases where alpha I is not zero, but the multiplication in this vector, the combination is zero.
So is it always equal to zero?
We are taking a condition. That's what we are defining. If we define it this way, if it is zero, a particular linear equation. If it is this way, if we define any this way, we define a linear equation. Any linear equation is ax plus by may be 3. But you can say x plus by minus 3. You construct any linear equation like this. So it's a sort of that linear equation. But the point is the multiplication by scalar. So if it is zero, different combinations of alpha I are zero, so it's straight, and the condition is defined as linear independence. But still, if it is zero, this means different multiplication the sum will be zero, but individual scalars will not be zero. So that's the point. So if it is the first case, we define it as a sort of so this was linearly dependent, and if alpha I xi is equal to 0, this means that alpha I is equal to 0 for each I, and the set this is called linearly dependent. So we have defined linear dependence and linear. So in linear dependence, any combination of this scalar with this vector spaces, this scalar may or may not be zero. Okay? But in case of linear independence, this is directly zero. So this minor subtle point, what does it mean? You got the point. So it has a very, because ultimately we are going to, once we solve these equations, we are going to extract the value of these scalars, how we define them. Got my point? So this is the important point we are going to see. For example, if we just follow the book, he's saying to gain insight into the meaning of this book. For example, if we take examples of some vector spaces, some vector spaces, where even though the linear combination of the scalars with the vector spaces, even though it's zero, but individually these scalars are not zero. The case of linear dependence. So how can we, for example, if we take, for example, if x and y are two vectors in C1 may be any complex, maybe number field or complex field. So x and y form a linearly dependent set. So if x is equal to y is equal to 0, so this is a trivial case. So this is 0, so it's a trivial case, so it doesn't matter. But if this now what we are going to say, so if we have, for example, yx plus minus xy, so this means this example, we can say we have an example in the relation that every set containing linearly is itself linearly dependent. So every set containing linearly dependent set is itself linearly dependent. So this is one example. Maybe this example will make it more clear. For example, if we take for example x will take 1 minus t, y will take t times 1 minus t, z will take 1 minus t square. So if you take a particular, you can construct n number of equations. For example, x plus y plus z, x plus 2y plus 3z, x plus whatever, in a very way, whichever. The linear combination of x, y and z multiplied by some scalars. Those scalars may be explicitly, if they are 0, then it's case of a linear independence. If they are not explicitly 0, they may have different values. Still, the value should get very equal. If it's still equivalent to 0, so we are interested in that combination for linear dependence. For example, if you see x plus y minus z, still this combination can become 0. You see, 1 minus t plus t into 1 minus t plus 1 minus, है ना, 1 minus t plus t minus t square plus 1 minus t square है. One of them may be plus. If it's minus, maybe ये minus है. This one is z is minus. This is minus. So this is minus. This becomes plus. So you see this, and this, and t and t will cancel. So it's 0. So for this particular combination of x plus y minus z, it's still 0. It's still 0. But it's not explicitly the scalars are not 0. If scalars are 0, the combination, this is 0. So explicitly, so that's a trivial case. Non-trivial case becomes that even if the linear, we have constructed a certain equation of this form, still it is 0, but it's not necessarily that individual these scalars are also 0. So this is the case of linear dependence. So if it is this way, however, infinite set of vectors, so now we can construct x naught, if you follow book, as x1 t. You can construct it at your place in a different form. So how is a linearly independent set? अगर ये linearly independent, if this is a linearly independent set, the previous was the linearly, it's a linearly independent set, that means alpha 0 x0, alpha 1 x1, alpha 2 x2, alpha and xn is equal to 0. So this means alpha 0, alpha 1, alpha n. So alpha may be 0 for any, or linearly independent. Whether alpha goes from alpha 1, alpha 2, alpha 3, it's a class of null sets, you can see it that way. For not for linearly dependent, for linearly independent. Or you can say alpha 0 is equal to alpha 1 is equal to alpha 2 is equal to. 0. Alpha n is equal to. So this is a trivial case. This is not trivial case. So you have combination of scalars with the combination of vector space. So which combination of scalars, the multiplication of scalars, which are not zero, but on the whole, the combination will become zero. That becomes more interesting for us. So why it becomes more interesting for us? If we just take, for example, normally we visualize space in terms of, for example, normally we don't visualize geometrically, we go n1, 2, and 3 geometrically, three-dimensional spaces. So in principle, mathematically, you can have n-dimensional spaces. So you can have if you construct if we have these vectors, we said that when we define vector spaces, we define numbers in terms of, someone would call, we use the word vectors. That's when we talk of finite dimensional vector spaces. The number fields, we use the word vectors with numbers. So if we have that intuition here, so how do we try to visualize? For example, if two vectors, so the intuition here is geometrical language. If you want to say the same thing in terms of some geometrical language, so what do you mean by that? How we define linearly dependent and linearly independent in terms of those vector spaces. For example,
How does this help us?
just two vectors are linearly dependent if they are collinear with the origin. This is one thing. And this is one statement. The other statement is two vectors. Now we go from 2 to 3. We can go inclusive from n, alpha 1, alpha 2, alpha n. So since we are interested in how this geometrical intuition will help us in visualizing things in vector spaces. So two vectors are linearly dependent if they are collinear with regard to that origin. For example, if you have number field, you can construct numbers in these number fields, which is some linear combination of some scalars. So how can we define two linearly dependent vectors? So that means they are collinear with the origin. So they are so if in the same way, if there are three vectors are linearly dependent, this means they are coplanar with the origin. And you can extend so on and so forth. You can have 3 plus 1 dimension, 4 plus 1, 5 plus 1. So any higher dimensional space will have an embedded space. Or a 2-dimensional space will embed 1-dimensional space, 3-dimensional space will embed 2-dimensional space, and 4-dimensional space will embed 3-dimensional space, and so on. And so in general, n plus 1-dimensional space will embed n-dimensional space. So if you have, so for a linearly independent or linearly dependent space, so these vector spaces, so how much you can extend I1 to any finite dimensional vector space, it's not. So for finding any finite dimensional vector spaces, I can go from, for this vector space, I goes from 1 to n. In the same way, the scalars can go also from 1 to alpha 0, alpha 1, alpha 2, and they need not necessarily be 0. If they are 0, then it's a trivial case. If they are not 0, so you can just accordingly construct these vector spaces. Now comes the another question. The question of, so this is how we define linear dependence and linear independence. Now the other thing is how we define linear combination. Linear combination means the way I said it in a number line. So if there are given set of vector spaces, how we can linearly construct them, which will span that space. So that finite dimensional vector space. So how we can have some, just like in a house, a building block would be a brick. So a brick is made of houses. A house is made up of bricks. You have a linear combination of bricks make a house. So in the same way, if you have a finite dimensional vector space, how we are going to have some elementary unit, and how we can linearly combine them to construct a finite dimensional vector space. So this is our job now. So how we are going to construct it is so what we are going to do is linear combination. So for example, we say xi is equal to I, alpha I, xi, and x is the linear combination. X is the linear combination of xi. So now there is a particular theorem for it, which you can write it, then we'll see. So the theorem sort of it sort of imposes, for example, if I write it, the set of. So again, I want to emphasize is that we shall leave the real proof that if x is a linearly, then a necessary substitution. So you can construct a linearly dependent set, just like I said, an n dimensional space is embedded in n plus 1 dimensional space, or n minus 1 dimensional space is embedded in, or 2 dimensional spaces can be you can extract it from a 3 dimensional space. Line can be extracted from plane. Plane can be the same way. So the same way, how we can construct a linearly dependent or linearly independent space, a linear dependent space from a linearly independent space in the same way. You can have that exercise. So in that context, there is a theorem. For example, the set of non-zero vectors x1, xn is linearly dependent if and only if for some xk 2 is less than or equivalent to k is less than or equivalent to n is linear combination of preceding ones. So set of non-zero vectors. So this is again vector space and finite set of non-zero vectors x1. So these are vectors is linearly dependent if and only if for some x key. So the value of this k should lie between 2 and n. It should be 2 less than 2. It should be greater than 1 and less than n. So this is what he wants to say. So we have to prove that set of non-zero vectors is linearly dependent. Is only, it's not dependent in some general sense. It's only dependent if it lies between the value of k. The value of k should lie between 1 to n. So this is a theorem. So how we are going to prove it? So the proof of this theorem is simple. So I'll write there's a two sentence proof of it. So if x1 and xn are linearly dependent, and k be an integer between 2 and n, and x1 and xk are linearly dependent. Now what the proof says, if worst comes to worst, our assumption shows that k is equal to n, and also the way we do in your earlier induction. Some statement is true for proof by induction. K is true for n, then n plus 1, and then we'll. So if we say if worst comes worst, if k is true for n, so we can define it for alpha 1 for x1 plus alpha 2 x2, so on, and alpha n xk, alpha k xk, sorry, is 0. And for linear dependence, alpha k is equal to 0. K can go from k is equal to 1, 2, and so on and so forth. And if you take one of them, alpha k, so if you just k, alpha k, you go to this way, minus alpha 1 x1 minus alpha 2 x2, so on. And so alpha k, you can go for denominator. Alpha k xk, sorry. So xk is equal to minus alpha 1 by alpha k x1 plus alpha 2 by x2 minus sorry, x2 by alpha k, so on, and minus alpha k by xk xk. So he is, we can take alpha k minus 1, k minus 1, k, it's alpha k. So this is the theorem. So this is a two-line proof. So I think I just implore you to think about it. Think about it in the sense that he has constructed a general Hilbert space. Sorry, not Hilbert space, any finite dimensional Hilbert space. And this alpha k, it's for k, but k is not n in that sense. So you take k here. But the last one, he has defined it as alpha k minus 1. So you have constructed one of the scale, this vectors, which is contained in this thing. So this should take it as a proof for that we can, the set of non-zero vectors is linearly dependent if and only if for some k it's a linear combination of these things. We have not, it needs a bit of more reading it twice, thrice, and trying to, what does it want to say? Got my point? So can we construct within the constraints of this k, line between this and then this, we can have a linear combination with a set of non-zero vectors is linearly dependent if and only if. So you can have a linear dependence only and if and only if it is if the constraint is between these two bounds. Got my point? So what we did, we first constructed some this general vector spaces, and then we defined it for this. So you just think over it. Maybe I'll just start. So now other point of the thing is how we constructed how we construct the basis of which this finite dimensional vector spaces is constructed of, which I said. How we construct a finite dimensional vector spaces from these different combination of bases. And those bases may be a vector space multiplied by this scalar. And those scalars may not always be zero. So if it is a zero, then we have a trivial case of linear independence of vectors. So if it is not zero, so how we can construct bases from those finite for those finite dimensional vector spaces. So how we have to construct the basis for these finite dimensional vector spaces, which is a combination of these scalars and vectors. So if I just define things, a linear basis or coordinate system is basically only to have that geometrical intuition which I emphasize. And linear basis or coordinate system in a vector space, V is a set chi of linearly independent vectors such that every vector in V is a linear combination of elements of chi. So a vector space V is a finite dimension if it has a finite basis. So this is important. So a linear basis in a vector space V is a set chi of linearly independent vectors such that every vector is a linear combination of elements of a vector space which is finite dimension and it has finite basis. So you can have a basis, linear basis can be only defined. So if we have those vectors and scalars, the combination of those vectors and scalars, alpha I, I can go from alpha I, xi. These different combinations of alpha i's and xi's, but they are finite. That has to be. So that, and if they are finite and their combination, then only we can define a vector space V is a finite dimension if it has a finite basis. For finite dimension vector space, this is the way we define things as basis. So for example, in a particular case, for example, if you define for example, if xn goes from xn t and n goes from 0, 1, 2, so on is a basis. Every polynomial is by definition. So you can have monomial, binomial, and polynomial and polynomial equation. Monomial means one variable, two variables. Just like we have a linear equation, one variable, two variables, three. The way we define matrix, how we define Ax is equal to, and then there are linearly dependent solutions, linearly independent solutions, no solutions, indeterminate. This way we solve. You can imagine we are basically doing the same thing what we do in the matrices, if you remember. How we define that augmented matrix, and then we have those eigenvectors. We are doing the same thing, but we are doing it in some general sense. So we have to define in terms of some vector spaces. So if we have any n-dimensional basis, which is like this, and further, for example, again, we can also have for example, if we follow the book, we use also something called Kronecker delta. Kronecker delta is what? Delta ij is equal to 1. If I is equal to, and it's 0 if I is not equal to. So for a particular combination of this thing, you can define Kronecker delta. So now what we have for I not equivalent to j. Sorry, I have just if I is equal to j, if I is not sorry, it's I is not equal to j, it's I is equal to j. So if we assert vectors in terms of x1, को हम ऐसे define it like this. x3, we can define it in terms of 0, 0, 1. Like we can have this thing, x plus y plus z. So we'll take only one variable, x, 0, 0. In the second equation, we'll take x, 0, y, and z. We can have this way. X, 0, 0, 0, y, 0, 0, 0. So if you have these sort of linear combination, you can, if you have to solve them in terms of these now constitutes the basis in that vector space. Okay? So for in the simplest case, so we can have x is like this, zeta 1, zeta 2, zeta 2. So you can have zeta 1 x1 plus zeta 2 x2 and zeta 3 x3, or x in C3, or C3 is maybe in complex space or real space, is a linear combination of them. So in general, for any finite dimensional vector spaces, we can define with the basis x1, xn. X can be defined as zeta I, xn. These are the different bases of those finite dimensional vector spaces. Now at the end, so we can have an argument. So at the end, I'll only read this theorem. Last theorem of this book, he is saying that if V is the finite dimensional vector spaces and y1 are the linearly independent vectors, unless y is already formed basis. So the way I said it, any n-dimensional space can be embedded in n plus 1 dimensional space. So in the same way, or any, for example, a dimensional space can be embedded in a higher dimensional space, 1 dimension. So you can extend the same argument for these different bases. So a base can be extracted from a higher dimensional base. So these finite dimensional vector spaces, these bases 1, 2, 3. So any given base can be derived from any subsequent base. That's it. That's what. So what if I just write it? So if I write these statements on the right with. So if these are any finite dimensional vector space and y1, yn is any linearly independent set of vectors in V, and y is only form a basis. y's already form a basis, we can find vectors. Ym plus 1. These are different bases. So what he said, what the theorem said, we can find bases m plus 1, m plus 2, m plus p, so on and so forth. So that totality of y's is also basis. So we can have y1, ym. So these are also bases. Ym plus p is a basis. In other words, any linearly independent set can be extended to a basis. Any linearly independent set can be extended to a basis in that general sense. Such that if, for example, y1, ym, x1 goes to xi minus 1, xi plus 1, it goes to n. So you can have from linearly so it's how we can arrive at linearly independent basis after doing finite set of operations. Okay, we can just like in a linear equation, you ultimately reduce the equations. For 2x plus 3y plus z, 4x. So you will reduce the number of parameters, and ultimately reach to some particular value. So in the same way, if we have an infinite dimension, constructed or finitely dimensional vector spaces, which is constructed out of those very bases. So how we can arrive at some minimum? If we have an n plus 1 dimensional space, how we can zero in for n dimensional vector spaces or n minus 1 vector spaces. So by finite series of operations or successions, this is what we have to say. So we at least read these from the book, which will make it more clear, and there are some examples subsequent to it. At least you read them. Even if you cannot solve, you can solve some of them in the first attempt. But if you are not able to solve some of them, but at least one should read them. What we find? For example, prove that this is a simple. 4 vectors form a linearly dependent set. The first. So 4 vectors like the book says, so you do it. This 1 0 0, y is equivalent to 0 1 0, z is equivalent to 0 0 1, and u is equivalent to 1 1 1. So in a C3 form a linearly dependent set. So you form a linearly dependent set. For linearly dependent set, it's a simple condition. Linearly dependent set, you have to construct an equation, a linear combination of them. Even the combination should be 0, but individually the multiplication of scalars and these vectors, they are not necessarily 0. Today we have constructed here an example of the same. So you do it in this example. And subsequently read the other examples. Here, stop.